Okay, this video is on, I think this will be video number 5 in terms of what I call the training videos. And this has to deal with normal distributions. I'm going to take a little different approach here. I'm going to go through a PowerPoint just very briefly and give you some kind of an upshot of normal distributions. But what I want to do primarily here is share a video with you where I work problems. So there's not going to be much going on here until we get into the graphing calculator parts. So guys, this is on normal distributions, things you should think about when teaching these to your students. First of all, notation changes. Okay guys, this is I think video, well, it doesn't really matter the number, it's on normal distributions. What I'm going to do here is just give you a brief introduction on teaching normal distributions to your students, and then we'll get into working some problems. So very little preliminary. We'll get through a few things and then jump right into using the calculator to teach normal distributions. So guys, first thing you've got to understand when you get into normal distributions is you're changing from samples to populations. Up until this point, the histograms that we have collected and we have prepared, I should say the data that we've collected that created the histograms that we prepared have come from samples. And we have talked about X bar and SX as the measures of center and spread. Today, beginning normal distributions, you will start talking about a population. The population histogram, if you will, is still described by the mean and the standard deviation, but we use Greek letters to designate the mean and standard deviation because we're dealing with a population. Very, very, very important distinction that people miss. I even hear my graduate students sometimes say that, I collected these measurements and they form a normal distribution. No, they don't. If you collect measurements and you create a histogram and it looks bell-shaped and symmetric, then you have a bell-shaped and symmetric histogram. When you move into a population, and remember guys, populations are comprised of many, 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 many measurements. Think hundreds of millions of measurements in many cases. You can't go out and collect that data. So I like to think of normal distributions as something that is theoretically created, theoretically driven. These things exist in theory, but we don't go out and collect normal distributions. We go out and collect measurements that may create a histogram that's bell-shaped and symmetric, but not normal distributions. On that note, sample histograms could be approximately bell-shaped and symmetric. Population histograms are perfectly bell-shaped and symmetric that we call normal distributions. So guys, here's a sample. Looks like we've looked at the number of people in a particular age group. These seems to be patients seen in a clinic. And we have something that's clearly bell-shaped and symmetric here. But because this represents a rather large sample, we call it a bell-shaped and easy for you to say, right? A bell-shaped and symmetric histogram. However, sometimes we get into populations where we can look at probabilities of group membership, and these things have tendencies where they are bell-shaped and symmetric, and we call these histograms, based on populations, a normal distribution. So combining them, really, I don't even know why I included this this slide, but hey, enjoy. Apparently, there's something really special about plating thickness. All right, guys, once we have a normal distribution, there's a 68, 95, 99.7% rule that plays an important role. And what you need to get over to your students there is, first of all, we have perfect symmetry. And from one standard deviation below the mean to one standard deviation above the mean, we have 68% of our data. And from 2 standard deviations below to 2 above, we have 95% of our data. And almost all the distribution, 99.7%, falls from 3 standard deviations below to 3 standard deviations above. Now, I would run through an example here. If I were you, IQs, normal distribution, mean of 100, standard deviation of 15. So I would run through an example after presenting this in general, look at some specific data. Another thing you're going to want to do is you're going to want to, let me see if I can pull my pen up here. You're going to want to bring up, what happens out here in these tails. Well, for some reason my pen doesn't want to work here. Let's see if I can make it work. Let's see if blue works. All right, so we want to talk about what happens in the tails. Well, you got to think about if you've got 100% of your data. I'll never pull this off. Sorry for the ugliness. And if we have 99.7%, guys, this is harder than it looks. Then we've got 0.3% of our data that has to go in the tails. Well, it has to be equally put into the tails, half of it here and half of it here. So what you have is you have 0.15% of your data in each of the tails. Well, 0.15% is, 15 out of every 10,000, which is, is not much. All right, gang, IQ scores, as I said earlier, they are described by normal distribution with mean 100, standard deviation 15. And we often abbreviate that to say IQs are N, capital N, stands for normal distribution. The first number is the mean, the second number, of course, is the standard deviation. So guys, if you look at the breakdown, you can see that the mean is in the center, meaning that half the people have IQs above 100, half the people have IQs below 100. One standard deviation below the mean would be 85. One standard deviation above the mean would be 115. So 68% of people has IQ between 85 and 115. Between 70 and 130, approximately 95% of the people. And from 55 to 145, we have 99.7% of IQs. So what percentage of IQs is above 122? What's below 108? What proportion is between 92 and 113? Guys, we're going to use what I call the P key, and I'll illustrate that in just a second. For percentages and proportions and percentile rankings, we use normal CDF. Normal CDF is easy because it requires 4 entries, a min, a max, your mean, and your standard deviation. So percentile rankings, something else that starts with a P, and it's essentially a percentile ranking is just asking you percent below, because percentile ranking is the percentage of scores at or below a particular score. So asking the percentile ranking for an IQ of 112 is equivalent to saying what percentage of scores is below 112. Guys, Z-scores, It's a standardized measure. And it's a way that we can compare a particular score in terms of its distance from the mean in terms of standard deviations. So we're standardizing it because we're dividing out by the standard deviation. Guys, positive z-scores tell you the score is above the mean. Negative z-scores tell you the score is below the mean. And in a very rare case where you get a z-score equal to 0, it tells you that the score is equal to the mean. So I'm going to show you in just a second how to calculate and interpret the z-score for an IQ of 112. Z-scores as a distribution, if we standardize z-scores from a normal distribution, we get a distribution that's also normally distributed with a mean 0, standard deviation equal to 1. So z-scores and raw scores, SATs follow a normal model, mean 1026, standard deviation 209. Find the z-score, find the percent of SATs above, and find the percentage of z-scores above your answer in part 1. So I'm going to illustrate these for you in just a second. Inverse norm key. This is slightly different. It's a different key and it has a different operation, different purpose. What I want you to think about here is think about the difference when you in the way the question is posed. Notice this is asking what score, what SAT score, what IQ score. What's the minimum SAT? It's not asking what's the probability, what's the proportion, what's the percentile. It's not asking you something that starts with a P. Well, for these types of questions for the calculator, we use the inverse norm key. And it only requires 3 entries. Percent below is a decimal, the mean, and the standard deviation. All right, guys, going to run through this with the calculator. So that's what's up next. I think it'll make this stuff a lot clearer for you to teach your students. Okay, at this part of the presentation, I want to show the problems that we saw in the video earlier, how we'd work these with the calculator. So the first thing I want to do, you can see that I have kind of a split screen going on here. On the right side, I'll essentially go through and answer each one of these questions using the calculator. So the very first thing we do is we may want to take a look at the distribution of IQ scores. That should be of IQ scores, not if IQ scores. So this actually becomes a little bit confusing to students. But sometimes they like to see a picture, so that's what I'm trying to accomplish here. So the first thing we'd want to do if we wanted to do this is go to y equals. So we go into our graphic editor. And if we'll come second function over to distribution, the first thing that we see is normal PDF. That stands for normal probability density function. So if I select that. Now, the x value in this case is going to be my x. My mu is going to be 100. And my sigma is going to be 15. Now, if I paste that in the home screen, or not in the home screen, but in the in Y1, this is what I get. So that should be to scroll all the way over and let you see that we have a normal PDF. Now the next thing I have to do is I have to come in and set my window appropriately. All we really need to do here is set the x-min and the x-max. Well, when we sketch distributions that are normally distributed, what we typically do is we start with the mean and go from 3 standard deviations below. Remember, the standard deviation is 15. And the maximum value we'll do is go from the mean plus 3 times standard deviation of 15. Okay? Now, next thing we'll do, we'll set x scale equal to 1. Now, in terms of y min and y max, it doesn't matter what we set these as long as the y min is smaller than the y max. Believe it or not, that can be a problem with students sometimes. What we're going to do, we're going to use something called zoom fit. And what it does is it gives us the best picture of the graph that we're trying to make based on the x min and x max that we've provided. So it's going to readjust the y min and y max to give us the best picture. Well, guys, we find that option under zoom, and if we go all the way to the bottom, oh wow. And come to zoom fit, which is just below zoom stat. Hit enter. It's going to do some calculations, and it will sketch the distribution of IQs. Now, I said earlier that this is a little confusing for students sometimes. Let me explain why. These problems that we're going to work over here, namely the ones that I'm highlighting now, problem A, B, C, D, and so on, where we find percentages and proportions, we're going to use normal CDF, the normal cumulative density function. So sometimes students get confused and they'll think that they've got to sketch the distribution of scores before finding the percentages. Well, you don't actually need to do that. For example, what if we had this problem and we just wanted to focus on the percentage of IQs above 122? Well, we really don't need all this information to do that. All we would need to do here is go to second function distribution, go to the normal cumulative density function. If we're wanting above 122, that means our lower bound will be 122. Our upper bound will be E99, which is the symbol we use for infinity. Our mean is 100. And our standard deviation is 15. Paste it. Hit enter. And our answer is 7.1%. Part B, what percentage of IQs is below 108? Same key. Again, don't let your students get sloppy and use normal PDF. This key right here is only if you want to see the picture. If you just need the answer to the problem, go to number 2, use normal CDF. In this case, we want below 108. So we're going to start out with negative E99, which is negative infinity. And that's really kind of not intuitively clear, because we probably have met some pretty goofy people in our life, but none of them has an IQ that's negative. That's not intuitively clear to students. It may not even be intuitively clear to a lot of professors. It's just what we do. Just let the students know that the people who have modeled IQs have taken all this in consideration. Even though we can't have an IQ below 0, we include the negative tail in our calculations. All right, gang, so do this. So percentage for part B would be 70.3%. So I'm going to go over here and make our answers. So this would be 7.1%. And the answer to the second question would be 70.3%. Get your students comfortable with rounding their percentage answers to the nearest tenth of a percent. Let's get real fancy here, just because I'm getting in that kind of mood today. Okay, gang, what proportion of IQs is between 92 and 113? Well, again, if you make it consistent here with your students, let them start thinking about this normal CDF key as your P key. So when you're asked to find things with, begin with a P, proportion, percentage, percentile ranking, you'll use this key. So we want between 92 and 113. All right. So everything else is set correctly. And guys, ultimately what we're trying to do here is we're just setting up the foundation for, once we get into inferential statistics, being able to find what we call p-values. So this is essentially the reason that we spend time on this at this point. Okay? All right, gang, so let's underline that. So the proportions are usually presented to 4 places. Again, percentages are reported to the 1/10 of a percent. Okay, part D, what is the percentile for an IQ of 112? Well, guys, percentile is just percent below. So again, it starts with a P. Use your P key. Percent below would go from -E99 up to the score, which is 112. And we will get the percent below. The only difference in percentile ranking and percent below is the way we report our answer. So our percentile ranking would be the 79th percentile. Now, the calculations would be the same if we were asked what percentage of IQs is below 112. But in that case, the answer would be presented as 78.8%, where the percentile ranking is to the nearest percent. Okay, the next one, find and interpret the Z-score for an IQ of 112. Well, we're going to use the formula, so the score is 112 minus the mean divided by the standard deviation. So we get a Z-score of 0.8. So let me get ready to underline this. So the Z-score is equal to 0.8, which indicates that an IQ of 112 is 0.8 standard deviations above the mean. Okay. Okay, changing things up a little bit now. Let's get into SATs. And what I want to point out in this problem is how essentially the Z-scores and raw scores are interchangeable. So let's just go through and see how this all plays out. So first of all, find and interpret the Z-score for an SAT of 1300. So I want to put in the score of 1300. Subtract the mean of 1026 and divide by 209. Now, a lot of times students will say, well, Dr. Darver, where are you finding that information? Remember, the number that comes first in this notation, the 1026 is the mean, and the standard deviation is 209. So, guys, the answer to part A would be, let's underline again. So the Z-score would be equal to 1.31. Z-score is a descriptive statistic measure, just like the mean, standard deviation, median, IQR, and so on. So they're rounded to 2 places, which indicates that an SAT of 1300 is 1.31 standard deviations above the mean. Okay? Now, what percentage of ACTs is above 1300? Well, come back to our calculator. We're asked to find percentage, so we use the P key. So we went 1300 up to E99. Well, I have no idea what happened there. Mean of 1026 and standard deviation 209. So guys, the percentage here would be 9.5%. Okay. Now, it's important that you let your students know that raw scores such as the SATs in this example and IQ scores are interchangeable. So what if we were to look at the same problem but look at it in terms of the distribution of z-scores? For example, this SAT of 1300 that we used right here to make this calculation has a z-score of 1.31. Now I'm going to get a little fancy here and show you a trick, okay? So let's go 1300 minus 1026 divided by 209. Now I want that, you might say, well, you already did that. I know I did that. But I want it right there so I have it in my last entry, okay? Now that's a z-score. Now if I go to my second function distribution and go into normal CDF, if I want to bounce this off the same problem I did in part B, what percentages of SATs is above 1300, I want to show that that's equivalent to asking or answering the question, what percentage of z-score that corresponds to 1300 is above. So I'm going to go second function answer, because that was the answer from the previous thing that I did in the calculator. Guys, the mean and standard deviation of z-scores is just equal to 1. And what students will see is that the answer that I got up here and the answer I get down here are exactly the same thing. So right here, same as part B. All right. Question number 3. What IQ score represents the first quartile? Now, in teaching this, you've got to get your students to kind of be aware that the questions we've done so far have been asked to find a percentage, proportion, or a percentile ranking. And when we get into central limit theorem, we're actually going to move that into where we find probability. But for right now, we want to keep it simpler to hopefully kind of minimize sources of confusion, if you will. So, but contrasting what we've been doing with percentages and proportions and so on, this question asks what IQ score represents the first quartile. Well, guys, the calculator key that we use in this case is not the normal CDF, but the inverse norm. So, inverse norm has a different form. First thing it asks is area. You've got to beat in your student's head, not literally, please, but you've got to beat in their head that this wants area below. It's just the way the calculator is programmed. It also wants the area as a decimal. So in part 3, what IQ score represents the first quartile? We ask ourselves, what percentage of scores is below the first quartile? And we should know by now that's 25%. We should also know that 25% as a decimal is 0.25. We're dealing with IQs, mean of 100, standard deviation 15. And I want to add here, I would not, if I were doing this problem, giving it to students, I would not present the question just as that. I wouldn't expect them to remember the mean and standard deviation of IQ scores. I would give that information to them in the problem. But we're not high school students here, so go on to paste. Hit enter. So the IQ that represents the first quartile would be 90. Now, students all the time are going to ask, well, Dr. Darborough, how am I supposed to present the answer? I'm a firm believer, or at least I'm from the school of thought, that we present our answers as our mean and our standard deviation are presented. So IQs, the mean and standard deviation are presented as 115, which are integers. So I would present the scores from that distribution as an integer. All right, part 4, or number 4, what SAT represents the 45th percentile? Again, you're looking for a score from the distribution. not a percent, proportion, or percentile ranking. So 45th percentile indicates that there's 45% of the scores below it, so as a decimal that's just 0.45. Remember the mean was 1026. And remember the standard deviation was 209. So these are presented as integers, so we'll put our final answer as an integer, so it turns out to be, well, I didn't know that, 1,000. Okay, now part 5 says a highly selective university requires its students to have an SAT in the top 7%. What minimum SAT will qualify you to be accepted in this university? If you think about the distribution, if we have the top 7%, that would be 7% of the area under the curve over to the right. So since the calculator requires you to put in percent below, we're going to need to put in 0.93. We're dealing with SATs where the mean and standard deviation are already there. Hit enter, enter again, and we get 13.34, not 13.34, 1334 as the SAT that would qualify or place you in the top, as the minimum score to still be in the top 7%. Now, a lot of people may say you need to round out to 1335. I'm okay with that. That kind of makes sense to me as well. So guys, that's all I'm going to do on normal distributions. We'll get into a lot more to normal distributions in the next part when we do central limit theorem and sampling distributions. So have a good one.